Okay, it's time to take this head apart. We'll start with the electronics. This thing just oozes build quality. If you just look at the detail of the cable entry, there's these. Basically, this is sort of the idea is this is a rotating joint. So we've got these sort of cast pieces that the cable comes into. You know, I don't know whether these are cast or just purely fully machined out of solid. They might actually, because of the low quantity of this, it may well be these are just machined out of solid blocks of aluminium. And each cable is actually crimped into these blocks, which provide both sort of electromagnetic shield termination, so you've got the electrical shields, or shield integrity from the cable to the outside of the case, but also mechanical support. So these are crimped on ferrules of various sizes, crimped to these sort of plates. Yeah, so there's sort of metal entry post that these are clipped round. Now, I'd imagine these are some sort of standard part. I suppose they could even be pneumatic fittings or something. I've never seen these before, but looks like these have been sort of press fitted into these pieces. I have already had this partly apart, which is why some of the connectors aren't plugged in, so I wanted to scavenge one of these high density D connectors to play around with that DPSS laser, which just coincidentally happened to use the same sort of connector, but apart from that I just sort of screwed it back on just to show how it goes, but not all the connectors are in there. So the most obvious thing is this unit here, which is marked stepper. Inside here we've got Xilinx CPLD XC95288, which originally I thought, oh, these are going to be stepper drives, but actually they are L2724 power op amps, which seems a little bit odd. On the other side there's some DACs and just sort of a few various analog op amps and analog stuff. I think what they may be doing is actually a traditional stepper motor uses basically on-off switching in combination with the inductance of the motor to provide the current regulation, so it's like a switch mode regulator. I think what they might be doing here is actually using analog current limiting for the steppers, because one thing that's a bit puzzling is you've got this massive heatsink, but obviously the motors in here aren't driving big loads, they're just sort of moving optical parts around, so the actual motor current isn't going to be that big, and certainly with a conventional stepper driver you wouldn't expect it to sort of need this massive great heatsink. So I think what they're probably doing is actually using linear current regulation to reduce noise, because obviously this thing's going to have sensitive optical detectors in it, so to avoid noise that you get with the switching on a stepper, they're actually doing everything sort of in the analog domain, so you know, burning off current from the point of view of keeping everything nice and quiet, which is not something I've seen done before. PTCs, which I'm guessing are probably just protection. And it may also be, it could be that, yeah, I don't know whether these are all going to be driving steppers, or maybe there's some other linear actuators in there as well that might be being driven from that. But one interesting little detail on a lot of these boards, they actually say things like the actual layer count and the technology, you know, the line pitch, and designed by JP. I don't know whether JP is a person or a company or a department. But most of these boards, they've got things like all the layer counts. Interesting, these are all, a lot of these. For example, there's quite a lot of annotated test points and so on, but it's interesting they're done in the copper layer and not in the silkscreen layer. I don't quite know why that would be. There's quite a few labelled test points on a lot of these as well, which is quite nice. Again, these are all obviously done either in-house or sub. Yeah, they're all got Leica microsystems, and actually there's a connector on there, which is, I'm sure that's going to be for test. Yeah, that's not accessible from outside, so that's clearly just going to be a sort of probably test and maybe JTAG. Although there's also some connectors here which may be JPEG, but maybe perhaps that's for test or perhaps expansion. Maybe perhaps they use this in other products and something else plugs into there. Another, again, piece of over-the-top construction. This is the actual air duct that takes the air from that blower we saw in the base unit to duct it into some part of here. And again, this is a fully machined piece. This isn't like something that needs to be rigid for optical stability. All this is an air pipe. I mean, they could have just used a piece of plastic for this, but this is a couple of pieces of quite complex machining purely for blowing a bit of air through. I don't think, I mean, it's possibly might also have some role for mechanically supporting the back panel, but does seem somewhat of an overkill. Right, so this is the rear panel, so I've already unscrewed. Take a few of these remaining plugs out. And this thing must have been a real fiddle to put together, because it's very densely packed, there's very little space, and there's a ton of cabling in there. So this board is just basically handling interconnect between all the rear panel connectors and the internal one. There's power distribution, some capacitors on the power supplies, some LEDs on each power rail, some protection PTCs. These look like fusible resistors, so again this is probably protection. But it's interesting, this board has got surface mount and through hole parts on both sides, so obviously a little bit of a challenge to assemble. Just looking at the joints, it looks like this side was flow soldered, so this side would probably have been hand soldered or possibly done on a selective soldering machine, but considering this thing would have been pretty low volume, I'd imagine they probably just hand soldered these, so there's these connectors and these ones down here as well. All the connectors and everything are labelled, it's in some cases in the copper, in some cases the silk screen. And it says here again, sort of 4 layers, 0.2 mil, I assume that's 0.2 millimeters. And also warning 70 microns, this is obviously done in heavy copper, so just sort of Achtung to warn you that this is a non-standard thing for the PCB manufacturers, and again designed by JP. If anybody knows who JP is, or if you're JP watching your work being torn to pieces, please get in touch. Right, let's get some of this cabling out of the way. Right, first thing that strikes you is just the fact that there's just tons and tons of board. They just seem to be sort of wrapped and folded around. There's sort of 3 boards all in various stacks. Unsurprisingly, some of these, not all of these are screwed down. I don't know whether that's because they were never screwed down. In fact, actually, there's what looks like there was a screw there, so maybe some of this has been apart and they didn't put the screws back. But there's quite a few sort of these plug-in boards, so that plugs on. That's just 2 serial ports that go into the RF control, modulator control units in the base unit. Board on here, which just has got a load of RAM on it. So this board, this is an LSI 53C770, which is a SCSI controller, so this will be the interface to the host PC. So this whole thing was clearly a SCSI peripheral. So we've got SCSI connector there, transceivers, RAM over there. It may well be this could actually be a fairly general purpose interface board that perhaps is used in different systems. The style is slightly different. We don't have those sort of layer things, so this may have been either done by a third party for Leica, or perhaps just done by a different department to the rest of it. And micro that's pretty like an embedded operating system. It's a 68 EN360, so it's pretty much 68,000 series processor, so this may well be a fairly general purpose processor and interface board that then gets used in various different instruments. And it's copyright 1999, and there's a few 2000 date codes there, so around sort of 2000-ish. Board here, this is an interconnect. So this little piggyback board onto this one here actually says regulator board. A lot of analog stuff. Most of this is analog switches, D to A converters, some op amps. So this is all analog stuff that says regulator. Maybe this is reducing various sort of reference voltages and the like. Again, PCB held in by this custom machined aluminium bracket, and some power devices screwed down here, and there's a sort of chunk of metal with some heatsink goop on it, which is obviously to couple the heat from this heatsink back to the back panel. Right, so we've got another stack of 2 PCBs. The top one, which says Z driver shutter board. Another Xilinx CPUD on there. Again, just tons on every other chip's analog devices on here. So it's all going to be analog A to Ds, D to As. Load of linear voltage regulators. There's a power op amp there. Again, all linear, all sort of, no doubt, low noise. And this plugs into here. Again, we've got a couple more of these L2724 power op amps, a couple of linear regulators, another Xilinx CPLD, This is just says driver board. Again, we've got the legend on here, which is 8 layers, 1999, and all this is designed by JS, so obviously JP's mate. Sharing the load, a bit of bodgery here, capacitor put over, bodged on the top. It's a bit disappointing they've not actually stuck that down, that's sort of floating around a bit. And some bodge wires. Obviously these things are made in very, very small quantities, so it would be pretty much out of the question to do a rerun of a board just for a few mods like this. These are as long as it's reasonably fixable, they're going to fix it rather than redo the board. Especially on an 8-layer board. It's going to be quite expensive to get redone. There's a bunch of polyfuses, some LEDs down there. There's probably just power indications. And I just looked up a random selection. These are pretty much almost all D to A converters or analog switches. There's one A to D converter, but it's lots and lots of different D to A, lots of analog switches, op amps. This is all sort of analog, very, very analog stuff. Once we get deeper into the optics, we might get a better idea of what all this stuff's driving. Right, a couple more boards left. This one says mainboard SP2. A few these big chips are static RAM, a couple of DC to DC converters. Down here for power. Wow. 2 massive great FPGAs, Xilinx XCV300. Incidentally, this appears to be where that ducted airflow is coming in, so the air comes in here and then goes through here and then out the side. So again, this is a sort of solid machined mount, so this is where a lot of the heat's being generated in these FPGAs, so they've actually got this airflow. Interesting, they haven't got any heat sinking on here. Also on here there's a couple of CPLDs and a load more analog stuff down here as well. So we've got FPGAs with just RAM chips dotted around, three different oscillators, Xilinx CPLD down here. And this one's designed by BW, so they've got at least 3 people working on this. Actually some text in one of the inner layers. It says VCC2V5 plus MEL detector power, so that's probably the actual function of that particular layer on the PCB. Now, I can't see a layer count written on here, so obviously whoever BW was wasn't that keen on putting layer counts on his PCBs. There's some unpopulated sections there for something or other. I don't know if those are maybe RAMs or configuration memories or something. They seem to connect sort of between the two, so maybe perhaps have FIFOs or something for handling data going between them in various in other versions. And these down here are a couple of FIFOs, so these would have handled buffering of data between this and the rest of the system, maybe to the SCSI interface of. I imagine these DC-DCs are probably to provide the low voltage core supplies for the FPGAs. Doesn't seem to be any other regulators on here. Yes, it says UNR 2.5 and 3.3. These are fairly old FPGAs, so 2.5 may be the core voltage on these. I can't be bothered to look those up. And there's another board down here, 2 CPLDs. There's a load of high-speed A to D converters. ADS805s and some analog stuff, so it looks like there's 4 sections, so I would think this is probably the stuff that processes the input from the detector, which I think is probably photomultiply detectors. So this will be what takes the scan data in to produce the image. Just take this out of the frame so you can see anything in a minute. So on the other side we've got this little power supply section. Yeah, it says detector board, 8 layers, 1999. little bodge wires there. In fact, yeah, it looks like this is 8 channel. We've got basically the same circuitry on both sides of the PCB. So each of these connectors would be 2 channels. This is the sort of legends on all the power connectors, pinouts, and this one designed by JS again. Now the cables from that detector board disappear into this grey thing here, so I'm guessing we've got some more electronic goodness in here and probably some photomultipliers. Little unit with a couple of lenses in there and another section, and some couple of motors and some bits and pieces in there we'll look at in a minute. Board in here with a couple of things labelled with our old friends Hamamatsu, so these are going to be photomultipliers, some little bit of amplification stuff down here. Might be a power supply, high voltage power supply in here as well, because again for low noise you want to keep your power supply nice and close to the detector, and you're certainly not going to be putting photomultiplier voltages down a piece of ribbon cable like that. Yeah, 700 to over a kV depending on the type of device. These look like quite small ones. Yep, so we've got our 2 photomultiplier supplies. Only one, there's one of these not fitted. I don't know if that was maybe either never fitted or it's been scavenged, but quite a neat little cute little plug-in photomultiplier tube there. And this, we've actually got the socket here, but this is a separate unit. This will be a resistor network, as photomultipliers use a resistor ladder to get a progressive change in voltage at each stage. So that's going to be just a divider network, which looks quite a fiddly little soldering job actually. They've soldered, yeah, these are actually both soldered, so they've soldered that connector in, and then they've soldered this in afterwards on top of it. Sort of high voltage symbols, and this one was by our old friend JS. And I'm guessing this one down here is probably going to be similar, if not identical. Well, it's not actually identical, they are different, but say we've got 2 photomultipliers in here. They're all the same, R9624, and again it could be that maybe they use different ones depending on the options. For example, what range of wavelengths they need to detect, but so these PCBs do have a few differences on them. You see that one says 2002, so much later. Maybe this is just a later version, perhaps it's got replaced at some point in its life. There's also a couple of options. I'm guessing those are for SMA connectors for a coax output. Again, this, yeah, maybe this board was used in multiple instruments as well. And unusually, these covers are actually made of plastic of some sort. There's some metallization in there. I wonder why they chose to make the, when they've made everything else out of machined out of chunks of metal. I wonder why they made these ones out of plastic. Sure, there must have been some good reason for it, but these have just got some fairly simple lenses glued in. By the time the light gets to here, because the photomultiplier is detecting over a quite wide area, I don't think these need to be particularly precise. The precision's all going to be down here in all the other slits. So it looks like these have got positionable slits here with some motors and so on them. And just take a quick look at the boards in the main unit, the laser box. This is just the rear panel. This is just all interconnect stuff. Again, it's got through hole on a little bit of surface mount on both sides. 4 surface mount parts on there. I'd imagine they'll probably just hand solder those. A few more, again, just power distribution, capacitors, diodes, probably for surge protection. It's designed by JP again. This board controls the RF generators for the acousto-optic stuff. So there's the various outputs: EOM, electro-optical modulator, acousto-optical beam splitter, UV vis, again presumably acousto-optical things to do with UV invisible lasers. There's an old Xilinx XC4020, very old Xilinx FPGAs, quite a lot of RAM, and a whole load of D to A converters, because these things, most of the inputs for this are analog voltages. Basically you set them up with up to 8 different RF frequencies, and it will mix those 8 frequencies, which correspond to 8 different wavelengths on the acousto-optical thing. So what this will be doing is just generating probably patterns of, a bit like a waveform generator type thing. Obviously there's quite a lot of RAM, presumably for storing the waveforms. I'm guessing output them dynamically. Yeah, AOTF DAC board. And this is BW again. Yeah, it looks like BW isn't keen on putting his layer counts on the board. That's looks like it's probably 4 layer. And this is the power supply out of the laser box. This is a modular supply. Obviously a big system like this has got all sorts of different supply voltages. So you've got 6.7 volts here, 24, plus minus 15, 12 volts and 5 volts. Now the way these work is, you go to the manufacturer, in this case Lambda. Generally I think the parts are pre-manufactured, but they then actually fit different modules, so each of these is a separate output module that they then fit at the factory, test, and probably give you your own part number for it. It's a 600 watt supply. So we've got these separate modules in here, and this is actually quite interesting. So you've got the common section on the left will be your input filtering, probably power factor correction, monitoring, rectifiers, and so on. Some of these, they actually have like a common DC bus, but in fact this is actually rather clever. What they've got this transformer, and then each of these modules actually has its own secondary winding as a piece of flat flex cable, because obviously the winding number of turns will be different for different voltages, and also some modules might have a single voltage, some might have multiple voltage. So so you can take all these different modules, transform obviously clamps together, so you stick them in the core, clamp it all together. There's some feedback from each module down to the PCB, so there's actually not a huge amount in each module. Filtering inductors, a little bit of control stuff. But that's actually quite a neat way of having identical front end for everything, but then different, all sorts of different voltages and numbers of outputs on the secondary. I'm looking a bit further into this. So we've got this is the 5 volt secondary that looks like it's got one turn on each side, and then we've got the sort of primary windings. It looks like there's sort of a set of windings interspersed between each of the secondary one, then the sort of top ferrite goes on, and then the spring clip secures it. And the last bit of electronics are these drivers for the acousto-optical things. Now there's 2 different types. As far as I can tell, I think this is just a later version. The functionality seems to be pretty much the same. This has got USB in addition to serial, but I have got some information through from these, so I will be having a more detailed play with these and the acousto-optical stuff in another video, but let's take a quick look at what's in them. Now what these do, they basically generate an RF signal in the order of around the 100 megahertz sort of region. I'm not quite sure what the outer limits of that are, but it's of that sort of region. It can generate up to 8 simultaneous RF signals which are mixed together, and each of those signals corresponds to one optical wavelength. And I think it can also control the amplitude as well as the frequency, so the amplitude controls how much of that wavelength gets through, and the frequency determines which wavelength. So you can control basically the mix of wavelengths and which wavelengths are passed through the filter. And I believe the output power is of the order of sort of high hundreds of milliwatts, as far as I can tell. And you can see we've got 8 identical vertical boards here. There's an old Philips 8051 series microcontroller. It's all sort of through hole on the main board. There's an 8-channel D2A converter and some buffers. RS232 transceiver here. These can be controlled either through RS232 or there's a plug-in sort of control panel with a little user interface and a little LCD on it, which I think that's mainly used for setup. Once it's been set up on these connectors, there's basically 8 analog inputs, and each input corresponds to one of the channels which you previously set up and tell it what frequency you want, and then you can just either turn on and off with logic signals or use an analog level to control the output amplitude. And on each of these boards is obviously one complete RF generator. We've got a frequency synthesizer. This is actually a synthesizer designed for TV tuner systems. That's probably the VCO down there, some filters, and a few other odd sort of bits of analog stuff. And then you can see how these are all summed to this single node, which then goes through to an RF amplifier stage and then to a final power amplifier. And this actually is a power amplifier designed for cable TV type applications. It's spec'd up to 550 megahertz. And he's also got something for thermal stabilisation. I'm not sure whether that's an input for, I'm guessing that's probably an input to tell it what the temperature is, but it also might be something like perhaps a reflected power sensing or something, so it can cope with the change in the optical characteristics over temperature. I don't find much information about that particular aspect of it. It's got a little fan in there. If we look at this second one, this is obviously a much more modern design. It's just a single surface mount PCB. There's no fan. This is all sort of designed for base plate cooling. There's now a PIC instead of the Philips chip. It's 18F450, so that's doing the USB interface. Got an RS-232 transceiver here. There's two analog devices, quad synthesizer chips, so this is clearly what's generating the signal, and there's some RF switching stuff here, some filters, a sort of a summing network, and again we've got some power amplification, probably some attenuation control. There's a DAC over here, which is probably to do with biasing the RF stages, and then we've got this nice fancy looking RF transistor for the main output stage. So it's sort of fairly clear that the functionality is similar, it's just a much more modern construction. So a fairly substantial pile of electronic goodies in here. So the next thing is to look inside the optical block, so that will be the next video.